This conference will now be recorded.
Very good morning, students. So we have been discussing Ampere's law and its application. So the last day we had discussed about solenoid, and this solenoid is actually a long solenoid. Okay, long solenoid. So how do we define a long solenoid and a finite solenoid? Suppose it has diameter 2a, small a, or let us say 2r, capital R, diameter r. So this r must be much less than the length of the solenoid. If the length of the solenoid is much greater than r, the radius of the solenoid, then it is called a long solenoid, or infinite solenoid also we can say. Very long solenoid, very long straight solenoid. So in that case, the magnetic field we have seen, magnetic field produced by the solenoid will be always along the axis of the solenoid, and the magnetic field at any point on the axis we have seen to be this, like oil inside. So sorry, this is magnetic field inside the solenoid on the axis. Okay, on the axis inside the solenoid. So this is actually, so everywhere, in fact everywhere inside the solenoid the magnetic field will be this. So that's why uniform magnetic field is produced by a solenoid. Uniform magnetic field is produced by a solenoid. Okay, and that value will be mu0 Ni. Mu, you know, that is the magnetic permeability in the free space. Small n is the total number of turns divided by length of the solenoid. Okay, and I is the current in each turn of the solenoid, or in each turn, current in each turn, current in each turn. So if I have n number of turns, capital N number of turns, so it is n into I. This is the total current associated with the loops of the, or coils of the solenoid. Okay, Ni. All right, this is good so far. But suppose I have a solenoid which has length comparable to the radius of the solenoid. So in that case, the magnetic field at any point inside the solenoid will not be this. It cannot be this. Okay, this has got a different formula, and in fact there is a nice derivation about that, but that is not very important in this standard. It is the stuff of BSc, so we'll not go to the derivation, but we can keep this formula in mind if sometime this numerical problem related to finite solenoid is coming, then we can attempt that. So this is BP at any point P inside the solenoid, magnetic field will be mu0 Ni by 2. Then this cos theta 2 minus cos theta 1. Cos theta 2 minus cos theta 1. Again, this P, if this P point comes here, okay, then what will be the case? So the kind of those questions we can ask. Okay, so if this point, say if this point is here, exactly at this P point is here, so theta 2 will be obviously 0. And what will be theta 1? Theta 1 will be 90 degree. Okay, theta 1 will be 90 degree because this line will come like this, like this, like this it will be. So this line, okay? Whereas this line will be exactly 0. Okay, theta 2 will be exactly 0. So thus we will get at any point this magnetic field, like magnetic field at edge of the solenoid, mu 0 ni by 2. This is the half of the magnetic field at the like inside oil inside the solenoid. Anyway, so we can say that this formula to be a general formula also. This formula can be a general formula also. So if the length is very very long, you look, this will be minus, see theta will be, see this will go like this, so it will be kind of, see this will be parallel, so it will be 180. So cos theta is 180 is plus 1. Okay, so plus 1 here. And what will be this one? This also will be 180. Sorry, this will be 0. Cos theta 2 is 0. So this will be 1 plus 1. So 2, then it will give you mu 0 ni. I hope you have understood this. I'll repeat this. Suppose this is the general formula for a solenoid. Okay, solenoid, and this is the formula for magnetic field produced by solenoid at any point P. See, the theta 1 is actually counted from here, axis to this side, and see theta 2 is counted from the axis to this side. Okay, this side like this. So if this length is L is much greater, okay, much greater, then this will go like this. It will, see, this will go and like a very very long distance. So then this theta 2 is going to be 0 degree, and this theta 1 is going to be 180 degree. Okay, so in that case, see, this will be 1, this will be minus 1 plus 1, so this will be mu 0 ni. If you look this, theta 2 will be 0 for a long solenoid. Okay, so if you put this 2, you will get eventually mu 0 is equal to small n I. Okay, so this is the thing. Okay, all right, we'll go to next topic. Okay, so before that, we'll just discuss how magnetic field vary. How magnetic field vary. Magnetic field for a solenoid vary with the distance. Okay, magnetic field at any point. Magnetic field at any point. So you have the solenoid. So as you know, we have already discussed that magnetic field will be B is equal to mu 0 ni when the point is oil inside the solenoid. Okay. Now if we go away from this point P on both sides along the axis of the solenoid, how does that change? So it changes like this. You look here, this is x-axis. So this is the magnetic field. See, magnetic field at the axis. Magnetic field just on the axis will be maximum, and on either side of the axis, it will decrease. Okay, sorry, this way. On either side, it will be decreasing. And see, this is the kind of graph we'll see. Okay, we'll be able to see. Okay, so magnetic field for a solenoid varies as this. At the center, like on the axis, it will be maximum. Then on either side, it will decrease. Now we'll discuss about another application of Ampere's circuital law, that is toroid or toroidal solution. Sorry, toroidal solenoid. Okay, toroid or toroidal solenoid. So what is this solenoid? Actually, this solenoid is kind of endless solenoid. You can consider an endless solenoid. So this is actually toroid means endless. So it is endless solenoid. If you take a solenoid, you have all the terms like this. Okay, if you just bend this, if you bend the ends of the solenoid, then what we get? And end and the like if you have a long solenoid, you just bend it in the form of a ring like this, so you will get a toroid, toroid or toroidal solenoid or endless solenoid. So in this case, see, the current is sent through each loop. This can be considered as ankle ring also, anchor ring, anchor ring, along with several number of turns, several number of turns. So anchor ring, toroid is actually an anchor ring. Okay, anchor ring along with conducting wire wound over it. Okay. Now, when the current is sent through the terminals of the toroid or toroidal solenoid, then what happens? Then there will be a magnetic field generated by these loops, and surprisingly, this magnetic field will be existing only in the hollow spaces of the toroid. See, only inside the toroid magnetic field, this also will be a uniform magnetic field up to, suppose this is R1, and if I draw another magnetic field lines like this at a certain distance from the center, this is at certain distance from the center, so say this is at R2. So this radius R2 is fixed, so the magnetic field, the value of the magnetic field will be also fixed. So magnitude, so here actually you will be able to find out or produce a fixed magnetic field, and magnetic field lines will be always inside the solenoid. Magnetic field lines magnetic field lines are actually concentric circle kind of, that is here. Okay, and you can see the magnetic field. See, this is the magnetic field line, this is the magnetic field line. So you can see the magnetic field lines are actually, this is here clockwise direction, in the clockwise direction, and the direction of the magnetic field at each point will be along the tangent. And see here, there is no magnetic field, neither magnetic field is there here, so that we have to prove. So we have to find out magnetic field at any point inside the solenoid, and we have to show that the magnetic field is 0 outside the toroid and inside the toroid, where there is, so not inside, uh, outside the toroid and in the interior space. Okay, interior space of the solid toroid, there will be no magnetic field. So let us find out magnetic field produced by toroid using Ampere's circuital law. So if we use Ampere's circuital law, first of all, let me remind you what is Ampere's circuital law. See, Ampere's circuital law states that line integral of magnetic field, closed line integral or maybe open also. So we'll write just line integral. Line integral means B dot dl. So this will be always mu 0 I, where I is the current enclosed by the Amperian loop as we have discussed earlier. Okay. So, and also we have seen this by symmetry, Ampere circuital law will be applicable only for symmetric magnetic bodies. So, or symmetric bodies. So, by symmetry, magnetic field will make magnetic field constant or fixed for a particular path. Okay, and then that could be taken out of the integration and see this. Okay, so B dot dl, and here, okay, so let us skip this here. Okay, so first of all, let us calculate the magnetic field or apply the Ampere circuital law for the space interior. Okay, interior space. So B interior, let me just take this P point here. So interior at P point, magnetic field at any point P. So how we will calculate using this Ampere circuital law. So let us say B is the magnetic field at that point, and dl then mu 0 into I enclosed we have to find out. So let me just take, see, let me take, okay, let me take this Amperian loop, the dotted curve what I have drawn here of radius small r, say small r. So here, what will be the magnetic field? Anyway, magnetic field along this circumference will be constant. So B dot dl is again 2 pi small r, and this is mu 0 I enclosed. Okay, enclosed. ENC is fine. Sorry. Now, see, this current enclosed this by this Amperian loop is 0, right? Okay, so current will be 0 because current is not passing through that. Okay, current is only going through the coils owned over the toroid. Okay, so net current or the current enclosed by this particular Amperian loop will be 0. So I enclosed 0 means here also it is 0, so B is 0. Okay, now we have to see magnetic field at the Q point. Okay, at any point Q, so we have shown you that magnetic field at any point P will be 0. That means at the interior space. So what is this interior? This is the interior space. Okay, this is called interior space where there is no current. If we draw a Ampere loop anyway, so magnetic field inside, I'll write interior. B interior is 0 or BP is 0. Now we'll see here, if we draw a Ampere loop, then see the magnetic current, see B anyway, this is all right. So B into 2 pi R, this is common. Now on the right hand side, you look here. See, this side current direction is into the page, this side out of the page. So if you just take sum of this current and this current, so it will be kind of minus plus of pi plus. This is 0. Okay, the current we're going to get like current enclosed by the Ampere loop is 0. So we can see the current enclosed is 0. Therefore, B dot dl or B into 2 pi r, that will be mu 0 into 0, that is 0. So where is magnetic field 0? Magnetic field is 0 at Q point also, or outside point. Okay, now if we consider, see, this is another Ampere loop. So Ampere loop we have already got here of radius r. Okay, and magnetic field, as you know, inside will be 0, outside also will be 0. There will be only magnetic field interior or inside the solenoid. So B into 2 pi r, let me write. And right hand side, see, if it is, see, like this at this position, so it is actually the position of the loop is, so magnetic field we have to find out inside the toroid. So this, you look, this Ampere loop only enclosing the positive charge. So you know this current, see, this is current which is actually going into the plane of the paper. So this current, like say if I have a solenoid like this, so in this case current enclosed is this much, this is positive current, because each ring when going like this, so at this position see direction change happens. Okay, so and also here, It is going into the plane of the paper. This is coming out of the plane of the paper. So this is, if this is minus plus and this is minus. Okay, so we have seen that the direction of the current changes when it actually getting wound over the coil. Okay, so here there will be enclosed current. So this will be just I enclosed by the solenoid. Okay, so B will be, so this also will be like, so this is, there will be R, right? There will be, if there are n turns, then n I enclosed by 2 pi R. Okay, and there will be obviously mu 0, as you know that. So mu 0 small n into small n into I. I'm sorry, this, I think this we have to take as capital N. So the number of turns will be this, and 2 pi r, that will lead to so n, L is equal to n by 2 pi r. Okay, so this could be directly written small n I, small n. Okay, so mu 0 is equal to, okay, so here also, in case of toroid also, what we get magnetic field as mu 0 small n into I. This is the magnetic field we get. Okay, all right. So what we have seen in case of solenoid and toroid, there are few differences and similarities we can see. See, in case of long solenoid, we have magnetic field. In case of long solenoid, so this is called toroid and this is for solenoid, say. So both are actually same. Okay, this is also number of turns per unit length. This is current in the coil, and here also the same thing. So BT also there is. Okay, so this is for solenoid and this is for toroid. This is one similarity. Second similarity, both are actually producing. See, in this case, differences. See here actually, magnetic field lines are circular. Circular field lines will be there. Circular field lines. Magnetic fields are actually circular in this form. Okay, in the toroid, sorry. And solenoid is endless. Sorry, toroid is endless, and solenoid there is a length. Okay, I'm sorry. This toroid is endless, right? So there is end for solenoid that we have seen. This is what I wanted to say. Okay, so we'll just learn one more thing in this part, that is magnetic force. Okay, magnetic force. Magnetic force on a moving charge, or force experienced by a moving charge in a magnetic field. So if suppose there is a magnetic field which is actually getting into the plane of the paper. So there is a uniform magnetic field where magnetic field is actually putting, like it is pointing downward or into the plane of the face. Now if you have a magnetic like point charge Q which needs to move with velocity, or which is moving with velocity v, and enters into this charge particle, sorry, it enters into this magnetic field. So what will be the force experienced by this charge particle? That is given by Lorentz, out of experimental facts, and it is said that this is directly proportional to the charge. Okay, the charge directly proportional to the charge force. So Lorentz said that the force is directly proportional to the charge. It is directly proportional to the magnitude of the velocity, or the velocity component which is perpendicular to the f, and the angle between the direction obviously matters a lot. So this is actually v sine theta. Now it is written as f is equal to q into v cross b, or v sine theta. Okay, v sine theta. Okay, this is the force experienced by a such particle which is called Lorentz force. Obviously, Lorentz force is referred to as the sum of the electric and magnetic forces. Okay, so but one thing is very important, that magnetic field here. See, if there is a static charge, there is no. See, if there is a charge sitting inside the magnetic field, is there any force experienced by the charge particle E? No. Okay, so this is about magnetic force on a moving charge, and if the charge is static, there is no force on that. Okay, so I think we'll stop it here for today. Next day we'll learn about magnetic forces, cyclotron. Okay, principle of cyclotron, etc. We'll learn tomorrow. Okay, so thank you for your patience. Bye for today.